The most missed questions from the functions GVC test were numbers 2, 5, 6, and 7. We're going to go through each one and talk about how to solve an example. Number 2, we have to find either the local maxima or the local minima of a function that's been graphed. So the blue line represents that function. This time it's called function f, but the letter really doesn't matter. The maximums are going to be the higher values, and the minimums are going to be the lower values. This one wants us to find the maximum values. When it says maximum value, it's talking about the y number for the coordinates of the points where we have a maximum. It also wants to know the values at which f has a local maximum. That means where are the maximums, and so it's asking for the x values for the coordinates of those points. On our graph, we've got two high points, -2, 0 and 2, 3. The lower points are minimums, and we are not going to deal with those for this question because it only asks about the maximums. The y values for our maximums are 0 and 3, and then the x values of our maximums are -2 and +2. For number 5, we have to identify the table of a function as being either linear, quadratic, or exponential. A linear function will always have a common difference when you subtract the y values. And a quadratic will have a second difference that is always the same. And an exponential function will always have a common ratio, which means it multiplies or divides by the same amount each time. Let's see how to check each table. For function number 1, we first would subtract the y values to see what the difference is between the first two. In this case, -20, since it's going down 20. We would subtract the next two values to see that now it's going down 15. We subtract the next two values, and it's going down 10, and we subtract the next two values, and it's going down 5. Difference means subtract, so to find the difference, subtract the two values. Since this one goes down a different amount each time, it's not linear. So we're going to check the second difference. We subtract -15 and -20 to see that that went up by 5. We subtract -10 and -15 to see that that went up by 5. And we subtract -5 and -10 to see that that went up by 5. This is called the second difference, and since it's the same, 5, 5, 5, this is a quadratic function. Once you find the answer, you don't have to worry about checking for the rest. Let's go on to function 2. We're going to start by checking to see if it's linear by subtracting the function values for y. If we subtract -48 and -96, we can see that it's going up by 48. The next two values go up by 24, the next by 12, and the next by 6. Since those numbers are not all the same, this is not linear. Now we're going to try and see if it has a common second difference. We subtract 48 and 24, and we subtract 12 and 24, and we subtract 12 and 6, and we can see that those numbers are not the same. So this is not quadratic. Now we have to check and see if it's exponential. To check if it's exponential, if it's timesing by the same number each time, we have to divide the y values. First, we would divide -48 by -96, which is 1/2. This means it times by 1/2, or divided by 2. Next, we would divide -28 and -48, which is 1/2. We divide -12 and -24, which is 1/2. And we would divide -6 and -12, which is 1/2. Since the ratio is the same for each set of y values, meaning it's going down by timesing by 1/2 or dividing by 2 each time, this is exponential. So you would subtract to see if it's linear or quadratic, and you would divide to see if it's exponential. On function 3, we're going to start by checking to see if it's linear by subtracting the y values. This one goes down 11, then goes down 11, then goes down 11, and then goes down 11. Since it has a common difference, goes down 11 each time, this is linear. For number 6, we're looking at an exponential function. We have a formula for the exponential function. F of x equals b times r to the power of x, where b represents the y-intercept number and r represents the ratio number. If we look at our equation, we can identify p of t, different letters but still okay, equals 1,500, which is our y-intercept, times 1.019, which is our ratio, to the power of t. First question wants us to find the initial value, which is just the y-intercept, and so is 1,500. Next, it wants to see if this is a growth or decay function. We have a formula for that. The formula to find the percent of growth or decay is r minus 1 times 100, where r is the ratio. In this case, our ratio is 1.019. Now, when we plug the formula in, if our answer is positive, this is a growth, and if this answer is negative, it's a decay function. We're going to do 1.019, our ratio, minus 1 times 100, which is 1.9. Since this is a positive number, it's a growth function, and the percent of growth is 1.9. The last question, number 7, is finding the domain and range for an exponential function. Remember, domain is the x values, and range is the y values. We're going to use the x and y axis to identify the domain and the range. Every exponential function is going to have a horizontal asymptote, which is a horizontal line showing where the function does not go past. In this case, -3 on the y-axis is what our function does not cross. It will get closer and closer to -3 but never actually reach it or go past it. This means our values for y are always going to be above -3, so our range is y is greater than -3. So if our function is above the asymptote, we would use greater than. If we ever had a function below the asymptote, we would use a less than symbol, but we don't. The domain is the x values, so we would look at the x-axis and see how far our function is traveling to the left and to the right. Since it keeps going both directions, our domain is all reals, which means it could be any number. It keeps going both directions and does not have a point it cannot cross.